Why is grasping the concept of molecular dynamics so crucial? And how do force fields contribute to this understanding? Today, we delve into the fascinating world of molecular dynamics simulations, a computational technique that studies the dynamic behavior of molecular systems over time. In the heart of these simulations, we find force fields. They act as the compass, guiding the journey through the molecular landscape. Force fields define a molecular system's potential energy based on the positions of its atoms. They provide the rules of the game, so to speak, offering a set of parameters and equations that govern the interatomic interactions. This allows the motion and behavior of molecules to be modeled with great precision. So what makes up these force fields? They consist of various components, each corresponding to different types of atomic interactions. Firstly, there are the bonded terms. These include bond stretching, which describes the extension of chemical bonds, angle bending, covering deviations from ideal bond angles, and dihedral angles, modeling rotation about a bond. Then we have the non-bonded terms. Van der Waals interactions, or Lennard-Jones potentials, model short-range attractive and repulsive forces between atoms. Electrostatic interactions, on the other hand, describe long-range interactions based on Coulomb's law. Among the popular force fields we have charm, amber, gromos, and OPLs, each with its unique strengths and commonly used for specific types of molecular systems. Now, how do these force fields work in practice? The process starts with parameterization, where force field parameters are derived from experimental data, quantum mechanical calculations, and thermodynamic properties. Then comes the energy calculation, where the potential energy of a molecular system is calculated based on the positions of atoms and the force field parameters. Finally, Newton's equations are solved numerically to update the positions and velocities of atoms over time. The importance of force fields is profound. They allow researchers to represent complex molecular interactions in a computationally efficient manner. They enable the prediction of structural and dynamic properties, providing insights into the structural changes, dynamics, and thermodynamics of molecular systems. They play a crucial role in simulating the interactions between drug candidates and biological targets, aiding in drug design and optimization. They are also invaluable for studying biological processes such as protein folding, ligand binding, and conformational changes. In a nutshell, force fields are the unsung heroes of molecular dynamics simulations, bridging the gap between experimental data and theoretical predictions. Choosing an appropriate force field, keeping in mind the specific characteristics of the molecular system being studied, is vital. Researchers must be cognizant of the limitations and strengths of different force fields to ensure accuracy. So the next time you contemplate the wonders of molecular dynamics, remember the force fields working behind the scenes, making it all possible.